Hi, everybody, and welcome to the second lecture for the semester, where we're going to talk a bit about chemistry. By the way, I might mention, if you think you're crazy because you're hearing a bird, I actually have a bird. So I'm trying to use noise canceling microphone, but it is entirely possible that you will hear the dulcet tones of some background noise or another. So don't be too surprised. All right, so here we go with chemistry. Obviously, you're not taking chemistry, but if you remember from the last lecture, I said that we look at the different levels of organization. We start off with the atomic level. And many of you have had chemistry, and this will be super easy for you. But if it's been a long time since chemistry, or you don't remember what you learned the last time you had chemistry, this will give you a chance to review. Remember again that my PowerPoints are available for you on Canvas. So you have your own set available there to look at. All right, so I told you that the atom is the smallest unit of matter, and it is made up of different parts. And we can represent those parts in different ways. Here on the left side, you see one version. I've heard that called the planetary model because it looks a bit like you've got circulating satellites around a central location like you would the planet. And then this is one that represents the electrons in kind of a hazy manner. And that's actually trying to estimate where the electron would be found. Okay, but for us, what we're really interested in is how each type of atom is made up of different subatomic particles. And the three particles that we will see in this planetary model are the proton, neutron, and electron. And after the name of each part, you see a charge here. So protons have a positive charge. So if you're pro something, you're a supporter of it, you're for it, so that's positive. Neutrons, if you feel neutral, you don't really have a strong feeling, so that's no charge. And electrons, you can come up with your own idea for this, but they are negatively charged. Okay, and down here we've got a key, so you can see that the protons and the neutrons are found in the central area of the atom, and then the electrons are found, you can think of them in orbit around the planet. Okay, and then the electron cloud over here, it just kind of, I don't like this one as much because you can't see how many electrons are. All right, so we've got our proton, neutron, and electron, these terms you need to know. And then you can see down here that each type of atom has a different number. So our most basic style or design of atom is the hydrogen. And the hydrogen has one proton and one electron. You can see that it's lost, or I guess not lost, it doesn't have a neutron. So what's important too is that you have one positively charged particle, one negatively charged particle. So the sum, once you add a positive and negative together, is that there should be zero charge. Okay, then there's deuterium and tritium, which aren't really particularly important in terms of human anatomy. All right, now over here we see a breakdown in the human body of the elements that are most commonly found in the human body. So an element is just a large amount of material made up of one single atom. So over here, the element oxygen, right? Each of these is going to be an individual oxygen atom, and oxygen by body weight or mass is 65%. So if I could split you up into your different elements, over half of you would be made up of oxygen, followed then by carbon, hydrogen, and nitrogen. Okay, so even though nitrogen is only 3.2% of the body mass, it drops off after that: calcium, phosphorus, potassium, sodium, chlorine, and then into progressively smaller and smaller numbers. Okay, so the most common elements of the human body I would ask you to identify as oxygen, carbon, hydrogen, and nitrogen. Sometimes if I'm trying to memorize a list, I'll come up with a funny mnemonic device or a saying or something like that will help me to remember it. So how I've remembered this particular grouping for years has been to look at the first list, sorry, the first letter of this list in order, So oxygen, carbon, hydrogen, nitrogen. And I remember it as odd children have nightmares. Okay. So if you just remember the saying, odd children have nightmares, that will give you the 4 most common elements of the human body. All right. The atoms interact by forming bonds. And so once you form bonds between 2 or more atoms, that will create a molecule. Okay, very common molecules that we're all familiar with are things like carbon dioxide and water. And you can see these representations of shape are based on the interactions between these atoms. So if you're going to take chemistry or organic chemistry, you'll learn all about these. I'm not going to ask you about them here. Okay, but what I want you to know is that carbon dioxide, and looking at this formula, involves a total of 3 atoms. We've got 1 carbon and 2 oxygens, water, 2 hydrogens, 1 oxygen. Okay, so these are representations of molecules. These little molecules, such as water, have the ability to interact temporarily. So different bonds are going to lead to different types of interactions among the atoms. In anatomy and in biology in general, the chemistry of water is very important. And so you can see each of these is a representation of a water molecule. The big central part, that's representing your oxygen because it's much larger. And then the 2 ears, they look like ears on Mickey Mouse's head. These are hydrogens. And because of the size difference and the difference in the number of protons and electrons, these 2, when they make a bond, do not share the electrons equally, which leads to these slight positive and negative charges on the molecule and allow for the formation of hydrogen bonds. So hydrogen bonds are very weak bonds that form temporarily, but it does lead to some really unusual properties of water, like the fact that water expands as a solid. So if you've ever been silly enough to put a plastic bottle in your freezer, come back after it's frozen, the plastic bottle will have ruptured or swollen up because ice is going to occupy more space than water did when it was a liquid. Okay. All right. Now we get into some more important topics here in anatomy, the idea of very large complex molecules, such as you see viewed here. And honestly, it was a while ago I stuck this in here. It's obviously a protein, but I can't remember which one. But that's not really the point. The point is that this diagram shows each of these circles is an individual atom. So this molecule has many, many atoms that form bonds, and it takes on this really important shape. So macromolecules, the term macro, we've seen before, saw it in the last lecture, it just means large or big, or sometimes it's things that you can see with the naked eye. Sometimes it's just things that are much bigger than the other topic you're talking about. So a macromolecule is just a really large one. And it's large because it involves many atoms. Okay. All right. So how likely an atom is to form interactions or bonds with other atoms depends on its composition. So if an atom is likely to make bonds, we call this reactive. Okay, so it's going to interact with other atoms. So here on the left, we see an Na, which stands for sodium, and a Cl, which stands for chloride. And these 2 will interact and form a bond. And we would know that as salt, NaCl. That interaction occurs because sodium is eager to get rid of its 1 external electron. And the chloride is eager to gain 1 electron because it has an outer shell that is incomplete. Right, after they do that, they will take on a positive and a negative charge. And you've all heard that old saying that opposites attract. So you're going to have an attraction between the sodium ion and the chloride ion, and that's going to lead to a bond. All right, if some of this is unfamiliar with you, don't worry about it. I'm not going to get into the details of how many electrons you need in an outer shell or anything like that. Okay, But you should understand that certain types of atoms are much more reactive than others. And those reactive types of atoms are exactly the ones that make up our body, because our body is made of lots and lots of macromolecules. And you can't make a macromolecule if an atom is not reactive. Okay, in this case, when we're actually moving an electron from one atom to another, you make charged particles. So if it has a plus or a minus on it, it's got a charge, a slight positive or negative charge. And a charged atom is called an ion. The most important ion that we talk about in anatomy is the hydrogen ion, as that determines pH. And I told you before that the body, to remain in homeostasis, wants to have a constant pH in different areas of the body. Okay, so ions can be really important. So pH. The pH scale is a measure of these hydrogen ions. And there's a lot of information in here, but what I want you to focus on is really the pH scale over here. Okay, a pH of 7 was deemed to be neutral. And what that means is that the concentration of hydrogen ions is the same as it is in pure water. Okay, so distilled or pure water with nothing else in it has a pH of 7. So it has a certain number of these hydrogen ions in it. Okay, and pH 7 is pretty close to where we're going to find pH for much of the human body. Notice blood and semen, the number is slightly higher than 7, and that means we're moving in the direction of what we call basic. So any number above 7, all the way up to a maximum of 14 is basic. So in the human body, we find slightly basic conditions in some areas of the body. But then notice saliva goes the other direction. That's a pH, excuse me, of 6.5, which is slightly acidic. So any number below 7, all the way down on the scale to 0, means that it is slightly acidic. So saliva is slightly acidic, but the most acidic is the liquid in your stomach, your gastric juice, which is extremely acidic. So as we go through the body, I'll point out these areas of different pH because often it relates to the function, what's actually happening in that part of the body. So this highly acidic stomach allows your stomach to break the bonds holding proteins together. So later when we get into digestion, then you'll see how that works. Okay, saliva is a little bit acidic to discourage bacteria, and yet semen hates acidity, and so the sperm will not survive in acid conditions. So the ejaculate fluid, semen, is slightly basic. All right, so that's how the pH scale works. It's a measure of these charged particles, H+. Okay, the scale goes from 0 to 14. 7 is neutral, the equivalent of water. Any number smaller than 7 is acidic. Any number greater than 7 is basic. All right, now I want to go over the macromolecules of the human body. And there are 4 categories of these complicated macromolecules. The first one's something we're all pretty familiar with. You've heard the term carbs or carbohydrates. And in our body, carbohydrates are primarily used as an energy source. So you can have very simple versions of sugar known as monosaccharides. That would be something like glucose. Or you can go into slightly larger when you link 2 of them together, and that would be a disaccharide sugar. But a lot of our diet consists of these macromolecules made up of many of these repeated structures. This is starch, and starch is the primary energy storage macromolecule for plants. So carrots, potatoes, okay, loaded up with starch. This is one of the reasons we love potatoes so much, is potatoes filled with starch, and starch is just a whole bunch of sugars stuck together. Okay, so each of these green rings here is glucose. So when you break down a potato chip or a French fry or something like that, you're releasing a whole bunch of sugar, which your body will then turn into energy, okay? And if you hear my cat meowing, do not worry. He's not being tortured. He is just a very loud boy who likes to scream for his dinner, and it's about 45 minutes till he gets fed. So he will do this until it is time to eat. And I'm hoping the microphone is filtering it out. All right. The second category of macromolecules that are important in human anatomy are the lipids, which consist of all the fats, and less important in us, but more important in other biological organisms, are the waxes. Okay, so these are your fats. So how do you make a fat? Well, a fat is a pretty complicated macromolecule, but we know there are certain things about fats that are important, such as fats do not mix with water, okay? And so these are what are known as non-polar, and that means that any part of a molecule that is non-polar is going to be unwilling to mix with water. Okay, so what are the important lipids in the human body? Well, here on the bottom, you see an important one. This is known as a phospholipid. Now, this phospholipid looks a little bit like a sperm, actually. It's got a head, but instead of one tail, it's got two. Okay, so this molecule is what makes the outside of each one of your cells. So your cells are made up of a double layer of these phospholipids. And that composition being both polar, which loves the water, and non-polar, which hates the water, means that these molecules will organize themselves together in such a way as to form almost a skin or protective layer, separating the contents of the cell from the world outside. Above, we see another one, and I'm not going to show you a picture of these and ask you to identify them or something. I don't need you to memorize what they look like, but you should understand that a phospholipid is a type of lipid. Okay, triglycerides are another important lipid. These are the fats that you get from animals. So if you eat butter, or if you have a steak, something like that, the fats that are in there are triglycerides. Okay. So lipids are a very important energy source, but they are slow to digest, okay? But they contain more energy in lipids than you would find in the same weight of carbohydrates. So if you want a good energy source in your diet, fats are quite good, especially plant fats. If you eat a lot of triglycerides, that can alter your cholesterol levels and do bad things to your heart and to your blood vessels. Okay, the lipids in our body also include some sex hormones. Okay, testosterone and estrogen are made by starting with the lipid known as cholesterol. Okay, so we need some cholesterol in our diet. Take cholesterol and then you change it around a bit, you do some alterations, and you end up with sex hormones. So as we're going to see, most of the hormones are proteins, but some of the hormones, particularly those two that I mentioned, can be lipids. All right, our third and kind of the workhorse of biology are the protein molecules. Proteins are built out of amino acids, and there are 20 different types of amino acids. So the amino acids are kind of the small building blocks, the same way that glucose was the building block from starch. But now we have 20 different building blocks, 20 different amino acids, and you put them together and you build longer and longer chains of proteins, and they can be very convoluted and complex like the one I showed you earlier. Okay, proteins do most of the jobs of the body. Okay, for example, the antibodies. You've probably been hearing a lot about antibodies if you've been following the development of vaccines for against COVID-19. What we're trying to do is give people a shot that will cause them to make antibodies. And that will allow the body to quickly fight off, in this case, a virus. So antibodies are proteins. Most of the hormones, such as those that regulate your growth and those that control your sugar levels. All of those are hormones. Proteins also do things like transporting of oxygen. So if you think about hemoglobin, this is the protein that is found in your red blood cells, and it's the one that binds to oxygen and carbon dioxide so that those gases can be transported in your circulatory system. Sorry, I have to keep coughing, I don't know why. Okay, and then finally, we have what are called the enzymes. And enzymes catalyze reactions. What that means is they allow reactions to happen. Okay, so when we get into digestion, we'll talk a little bit about enzymes, but essentially enzymes are going to be important when you learn physiology. To recognize the name of an enzyme, look at the last three letters. If the name of this molecule ends in ASE, then you are talking about an enzyme. Okay, so lactase is the enzyme that allows you to digest lactose. So if you are one of the millions and millions of people out there who cannot digest milk products without getting gassy and feeling gross, then you might be lactose intolerant. And that happens because many of us no longer make the enzyme lactase once we're adults. Okay, so enzymes allow reactions to happen. All right, the fourth group of important molecules in the human body is not related to nutrition. These previous three groups I've talked about, having a lot to do with energy sources or building hormones, things like that. This is a much more limited group, but still very important. These are the nucleic acids. And you probably recognize this right here. This is DNA. DNA contains the information on how to make proteins. So as I said, proteins do almost all the work. Well, you have to know how to make them. The information on how to make proteins is stored in each of your cells in the form of DNA. Now, ATP, which stands for this long thing here, adenosine triphosphate, ATP is another nucleic acid, and it is a universal energy source used by your cells. So if you could imagine having a universal battery that would power everything from your smartphone to your home's air conditioning unit to your car. If you could imagine one battery that works on everything that needs power, that is the equivalent of ATP to your cells. So your cells, whenever they need energy, they have to have ATP. So we will talk about that when we get to cytology. If you remember, that is the study of cells. Okay, so when we start talking about how cells work, we're going to see where that ATP comes from. All right, now that was a very brief lecture, but packed with information if you're not familiar with these topics. If you've, like I said, if you've had chemistry, this is a really light treatment of the topic and you can whiz right through it. If you have not, or you need a little bit more time working on this, this is a good time to go and look up some of this information. Maybe review this lecture a few times. Okay, so it's a short lecture, and that is all you need to do for learning all this information. I hope to see you soon in Zoom, and I'll talk to you later. Take care of yourselves. Bye.